and thank you for joining us for the lunchtime. The title of the webinar today is Common Nutrient Problems of Spring Greenhouse Crops. Our speaker is Dr. Rosa Rodales, who is an assistant professor and extension specialist with the University of Connecticut. This webinar is co-sponsored by UMass Extension and University of Connecticut Extension. If you have any question during the webinar, please type it in the question box on your control panel, and Rosa will answer the questions at the end of the webinar. After the webinar, there will be a short survey. Please complete the survey before exiting the webinar. Now, without further ado, here is Rosa to continue with the webinar. Rosa?
Thank you, Geoffrey. Let me become a speaker. Okay. Can you hear me and see my screen?
I can.
All right.
Hear you, so I believe everyone is able to hear you.
Okay, so I'm ready to start then.
Okay.
So today I'm going to talk about top nutrient issues on spring bedding plants. And one of the things I always like to do is when I start a presentation is to make sure that I set your expectation from the beginning. One of the things that we're not going to talk about what the symptoms are or how to ID. Instead, we're going to talk about what are the true issues and what are the causes that are behind those problems, right? So just always have that as a perspective. That's what we're going to talk about today. So when we think about bedding plants, the main problem that we always can pinpoint to nutrient issues is either we have too much nutrient or too little nutrient. The cause is a different question, right? And in this photo we have on the left, we have a plant that is deficient on iron. So you can see that petunia leaf on your left. You can see that it looks like it's very hungry, right? And then on the right, you see that photo of that plant, geranium plant, and you can see that plant has too many nutrients, and the plant growth is suboptimal because it has too much nutrients. So it's very simple. When you're trying to train someone, or when you yourself are trying to identify a nutrient issue, you want to ask yourself, is this plant hungry or is this plant suffering from toxicity, right? Because the problems really just narrow in those two categories. What really we want to know is when we're trying to fix these problems or prevent these problems, more importantly, is that we want to identify the cause to prevent the problem. Because as we're going to learn today, a hungry plant doesn't necessarily mean that it's a system that doesn't have enough nutrients. It might just be that the availability is not where it has to be, right? Likewise, when we think about too much nutrients, it might not necessarily be that we're just applying too many nutrients when we're fertilizing. It might be an issue that's something that we're not applying, but that it's entering in the system. So just think about that. One is you narrow it down to try to figure out whether you have too much or too little, and then you trace it down to trying to identify the cause, right? And when we think about the causes, again, it's something that we can also narrow down to a very short list. One is that we have too many salts, and we're going to talk about what the sources of those salts can be. The other reason can be we have insufficient amount of fertilizer, right? So we know that if our plant's hungry, it's because we're either not applying too much or because the pH is off. So again, we're going to talk a little bit more about pH further, but the causes when we have a hungry or a toxic situation is because the pH is too high or too low. Okay, so again, very simple. Think about when you're trying to diagnose yourself, or think about when you're trying to train someone. That's the way you want them to think. If they see a problem, you want them to narrow down to these four potential causes. Okay, and now when we try to break that down a little bit further, we can think of what are the factors that affect this nutrient concentration and the availability that come from multiple sources, right? So all the inputs that come into that container are going to affect the amount of nutrient and the availability. And when I say availability, I'm typically talking about pH, right? So we can think about water-soluble fertilizers that we're applying. We can think about whatever pre-plant fertilizer is in that mix or you have applied. We can think about growing media and all the components of the growing media. We can think about irrigation water, and we can think about limestone, which I tend to always group with the growing media, right? So again, when you're trying to think about what's going on, you need to make sure that you're not thinking just fertilizers, you're not thinking just water, but you're thinking about how all these factors are playing this role of adding up in the container, right? So today we're going to talk about 4 different things. First, we're going to talk about checking new batches of growing media. We're going to talk about matching fertilizers to water quality and to crop needs. We're going to talk about monitoring pH and EC of the substrate, and we're going to talk about adjusting the fertilizer rate and type to manipulate the pH and EC. And again, you know the title of the presentation was Common Issues. The reason I chose to break the presentation this way is because these are the common activities that if we stay on top of them, we can actually prevent those nutrient disorders. The real problem is when any of these activities are not done, and then we're trying to catch up to solve the problem. So you can see these activities as a way to prevent the problem, or you can see these activities as a way of, I have a problem, I need to go back and make sure I go through all of this to try to see if I can rescue my crop. So the first one, and the reason I chose this first one to start is, in 2017, this was a very common problem. One of the common issues that we saw at that time was that the pH of the containers in the substrate was pretty low for a group of growers. So that led to iron and manganese toxicity. Specifically, geraniums tend to be the crop that suffered the most. As many of you know already, geraniums don't like to have too much iron or too much manganese, and that's why they like to have a slightly higher pH. So when that pH gets low, that's the group that's going to serve as an indicator that's suffering. And again, going back to, we're looking at the symptom that iron and manganese was the symptom, but we went back and identified that the cause is that the media did not buffer the pH. So this is an example of what happened a few years ago, right? And this is another photo of the problem. But one of the things that I want you to think about is that even though I'm giving you the example today of when the growing media comes, you might be using the same brand, you might be using what you think came at the same time, same batch or whatever, but you see that the crop is not growing the same. So it's just a good habit to make sure that you monitor the pH of the media. And I'm going to talk a little bit more on how you monitor that. And just be open about it and think about that even though 2 years ago we saw the problem of a drop in pH, I've also heard from growers having the opposite problem where the pH just keeps going up. It keeps going up, and they need to be pushing the pH down. So the problem can go up or down. And then in very few instances, this is not as common. It's probably something that I see more common with growers who are trying to use less traditional substrates, is that the electrical conductivity can be very high for some substrates. So many people are trying to use organic sources. Some of them, you need to make sure that you do know what's in there, because some of them are either too high in potassium or too high in sodium. So check the new batches, but be open in the sense that you want to know pH and you want to know electrical conductivity. Those are your 2 indicators that you're going to be tracking all through, and you start by doing that in-house, right? So again, those are just photos of one of the common problems in 2017, and just as a brief review of why pH can lead to so much problems, right? So we know that the pH of the growing media can affect nutrient solubility, and we know that when nutrient is not in the optimum range for your crop, that's going to affect plant health, right? Specifically, we're always mostly interested in micronutrients when it comes to pH, and that's where we tend to see the problems. So when you look at that graph, you see that iron and manganese, if you are between 5 and 5.5, you can see how thicker that bar becomes, and that's because the availability of that iron becomes higher, okay? And as the pH goes up, you can see that that bar becomes thinner, that means the availability goes down. So important to keep that in mind, and that's also very, very important training tip when you're trying to train your employees, right? Because one of the things they need to understand about the importance of pH is that elements like iron and manganese, you're applying them, they will be in the container, but if the pH is off, they become more or less available, right? So applying more iron in this example, if you're seeing a nutrient deficiency, might not be the solution, because you are then running into risk that you're putting more than what you can apply, than what the plant can take up. And then the other issue is also that if the pH comes down to the optimum, then you might end up with too much pH, too much iron, right? So it goes back to understanding the importance of the cause of the problem. An easy way to remember is that these elements go in opposite directions. So as the pH goes up, iron and manganese go down, and vice versa, right? So keep that in mind, like just easy thing to remember when you're training your team. So now when we think about the growing media and the components that will affect how pH reacts, we have to understand those primary components. What we use mostly in our industry is peat. So greenhouses mostly use peat-based substrates, and that peat is very acidic. So the pH of peat, once it has been processed and it's ready for growers to use, has a very low pH, right? So the growing media companies, they usually apply this limestone to make sure that there's enough limestone to react with the acidity that's inherently of that peat, okay? So even though most of us are truly not applying limestone to our growing media, unless you are someone who's mixing your own media, I believe most medium to small growers are not mixing their own media. Some large growers might be doing more of a mixing, but it's always important to understand how limestone works and think about it in terms of, if I was applying limestone, this is what it would be doing, right? So when we apply limestone, we have two fractions. One is something that's called a reactive fraction, and there's another fraction that's called residual. And that basically is what it sounds like. So if we look at this example, you look at that, what we're looking at is, if we have an impatiens plant, and we're growing that impatiens for 16 weeks, and that has some limestone in it, you can see that green line is residual limestone, right? So if you have residual limestone in the container, you can see that the pH will go down, but that limestone will continue to react, and therefore over time the pH remains relatively stable. And that's what most growing media companies aim to do with your media. When you buy it, they aim to have enough limestone so you stay relatively stable, right? If there's no residual limestone, meaning there's either not enough, or it reacted too quickly because of whatever acidity is entering into the system, you can see that there's no residual limestone and the pH would drop very dramatically. So just keep that in mind. And I think this graph is also one that reminds us of the importance of why is it that we need to monitor pH over time, right? Because you can have a situation where your media has some residual limestone, and your media is going to look like the green line there. But what if you have something that looks more like the red? If you just wait for the symptoms to show up, it might be too late by the time you're trying to push that pH up. You can probably push it up really quickly, but then it's the crop, the one that takes a little bit more time to catch up, right? So just think about that, and why is it really important for you guys to be monitoring what happens in that container. Okay, and then this one is one that it was originally done using applying media to applying limestone to the growing media, but it's one that you also want to keep in mind, as many of you are applying liquid limestone in your irrigation as a system, as a way to increase the pH. So what this graph is telling you, if you look at that red or purple bar, is the reactive limestone, right? And here we're talking about the same type of limestone, but basically it's how much reacts and how much is left after some time. So one of the reasons when we give recommendations about limestone is that it's better to apply multiple times a lower dose as opposed to applying one time a higher concentration, right? Because you have a little bit more of control. So let's say you're trying to increase your pH and you're applying the equivalent of 5.4 pounds per cubic yard. You can see that that's going to mostly get used up, right? If you apply more of that same limestone, you see that most of it's going to get used up and you're going to have some residual limestone, right? So as you keep increasing that rate, there's only so much acid that's going to react with that limestone, so a bigger fraction will remain as residual lime. So just keep that in mind as you're dosing. If you're applying liquid limestone, you want to start on the lower end, reapply if needed, because it's very difficult to just give you a number of a rate on how much you would apply, because you have to make an estimation of a chemical reaction, and it's very difficult to do that in a container. So the easier way would be I start applying a little bit, maybe I increase the dose if I see that the pH doesn't change over time. Okay. So one of the other things I've talked briefly about, it's important for you guys to make those measurements in-house. So one of the things you want to do is do a wet out test. And basically all you need to do is you collect your samples from multiple bags. It's important that you don't have just a single bag, but make sure you collect, depending how big you are, you collect from multiple bags, from new batches. You fill that out in the growing media. You're gonna irrigate as needed, but ideally you wanna cover the bottom of those containers to make sure that there's no leaching, because what happens is that when you're putting that water, then that kind of activates and turn on all the reactions that are going on in that container, and then you're going to measure the pH of the substrate over time. And this is not a real graph. I made that graph, but basically this is something that you want to keep track before you have a crop in your container, right? Because that's going to give you a good indication of what's going on. So let's say you have, I don't know if you can see my pointer. Let me see here. So you have a pH of 6.8 to begin with, and then we have a grower that has a pH of 5.3 to begin with, right? So if you start measuring every so often and see where the pH goes, it might be normal that the initial pH of your mix is a little bit on the high end, because that's, again, here is when you have a lot of the reactive limestone, and here the other explanation of this is that maybe the peat hasn't reacted with the limestone yet, right? So it's kind of normal to have those initial levels being a little bit off, but as within a few days, you should see that the pH should come in within your optimum range, right? So that's the goal here. You start with whatever pH comes up here. Don't get scared by your initial measurement. Instead, make sure that you're measuring things over time. If things remain, if let's say things would remain at 5.3 or go down, then you know you have a problematic mix. And same if it would stay here, but you know that within this range, you are relatively safe, right? But just make sure that you do that before the season starts, and that will give you a good sense of what's going on. You can also do this similar measurement as you're doing this with pH. Why not do it with EC? EC should not change over time. So the electrical conductivity is one that you can do a one time and it's a good indication, but not the same with pH. pH is one that you do want to do over time, okay? So at that time, when we talked about managing low pH, we want to make sure that we overemphasize this. When we see a problem the year before, the year after, that's all we're looking for. So make sure that if low pH is an issue in your operation, you try to understand everything else, and you don't focus just on the media, because that's what happened a few years ago, right? So you want to recognize the cause, and you want to think about what are the potential problems, right? So one is, if I buy a mix, could it be that the soilless media had a problem? If I'm applying my own lime, is it the type of lime or the rate that I'm applying an issue? Is water alkalinity a problem? And we're going to talk about that shortly. Is the fertilizer choice a problem? We're going to talk about that shortly. Is the crop a problem? So is probably the pH is not that low, but it's that this crop really likes it really low. And we're going to touch on that as well. Or is it that for some reason we're applying a certain type of acid and we're over applying? So again, make sure you break those down. You go back to all those causes before you're trying to fix the problem, okay? And ideally, you want to confirm that with a soil test. Again, you're going to start by doing something in-house, and that will give you a good indication of where you are going to make a management practice. But ideally, you want to send that to a sampling lab. And I just put the example of Yukon soil test, but just go to whatever company is the one that you're most comfortable with. And then alternatives to lower the pH. You also need to take into consideration other aspects. For example, if the electrical conductivity is high, then you want to make sure that you're irrigating with clear water first, because if you're going to be applying limestone, the limestone will have an effect on electrical conductivity. So you want to wash your salts a little bit first. You want to make sure that you're discontinuing anything that's acidifying, and that would include any fertilizer that can be acid. And again, we'll touch on that a little bit soon. You want to start feeding your crop with a basic fertilizer, and two good examples are 13-13, which is one that's used for plugs. So you can use that one. That tends to be low in some of the elements because it's designed for plugs, but it's a very good option. So you would have to ramp up your rate maybe. And then 17-4-17 is also a relatively basic fertilizer. You can also apply flowable limestone or potassium bicarbonate. Many growers find this as a good option. But one of the things that I want you to think about is when is it that you decide between, do I just use a basic fertilizer or do I start applying flowable limestone? So here are some rules of thumb here. So let's say you have a group like geranium that likes a higher pH. So likes a pH between 6.0 and 6.6. If your pH is between 5.8 or 6, then your management practice should be, I'm going to apply a basic fertilizer, right? If your pH is under 5.8, meaning the pH is much farther than the optimum, then you can think, okay, I'm going to apply injectable flowable lime. And one of the things I want to encourage you is to always think about using the fertilizer as your tool first, and then think about using things like acid or limestone, right? So that's your kind of your second layer of tools. Your first layer should always be your fertilizer. So if you have a crop like a general crop, say like a poinsettia, you know that the target is between 5.8 and 6.2. You can apply a basic fertilizer if your pH is between that range there, or if the pH goes under 5.4, then you can consider that you should be applying flowable limes. And then with petunia, the crop's much happier at lower pH. So let's say that depending on the cultivar, your pH, the optimum pH is 5.4 to 6.2. Let's say if your pH is between 5.1 and 5.4, you might just want to apply a little bit of a basic fertilizer to make sure that it doesn't keep dropping. But of course, if the pH goes way too far from even how low petunia likes it, then you can think about injecting flowable lime. But this is a good example. Just think petunia doesn't like it to have the pH too high. So your first tool should never be to apply flowable lime. Instead, you just use the fertilizer, which is a slower way to raise the pH, but it's one that it's less aggressive, right? When it comes to applying flowable lime or potassium bicarbonate, a few years ago in the University of New Hampshire, they did this test and they came up with the rate of, if you apply flowable lime at 4 quarts per 100 gallons or potassium bicarbonate at 2 pounds per 100 gallons, then it can increase your pH by 1 point. So that was a general trend. Calcium carbonate, I don't have a lot of personal experience with it, but basically I've heard a lot of growers being very happy with the product, so you can follow the label rate. And similar to what I was saying earlier, always start with the low rate and play with it a little bit as you're increasing. And with most of these liquid type of limestones, you always want to make sure that you, if possible, you want to avoid applying it on the foliage, because you can see that the foliage gets covered by that limestone itself. It's not a terribly bad problem, but you would have to make sure that you rinse those leaves after the fact, right? Because if they stay for too long, the calcium can harden or can damage the leaves. So that needs to get rinsed to make sure the crop looks well. Okay, so now we're gonna swap to matching the fertilizers to water quality. So it's always very important to think about that most of us are applying water-soluble fertilizers. So everything that goes in the water and it gets mixed with the fertilizer, it's going to reach your container. So that tells you a lot of things about the type of fertilizer and the amount of fertilizer that you're going to choose, right? So first thing, everyone, no exception, non-negotiable, everyone should test the water quality, right? So you want to make sure that you get a water irrigation suitability test where you get all the essential elements for plant growth. You are also going to get pH, alkalinity, total electrical conductivity, and as a standard, most of these companies, they also measure sodium and chloride for you, or aluminum. So just make sure that you pay attention to all those, okay? So how do you analyze this water quality test when you get it? First thing is you want to look at the alkalinity. That's going to help you decide the type of fertilizer. So alkalinity, the easiest way to think of what alkalinity is think if I had dissolved limestone in my water, that number is the equivalent to alkalinity. So similar to what we were talking about flowable limestone, it's the equivalent. Everything that will react with acidity, it's the number that adds up into alkalinity. You want to make sure that you check the total and individual ion levels, because you want to know if you have too much calcium. So if you have too much calcium, you're going to adjust your fertilizers based on that, right? And you want to make sure that when I say total levels, you're going to look at the electrical conductivity, right? That's going to give you a sense of, is it too high? If it's low, it means that it's very pure, so you basically don't worry too much. But if it's above 0.5, you know that there are some elements that are going to be relatively high and that you might need to adjust your fertilizers there. Okay? So why do we talk about alkalinity? It's because alkalinity is a stronger base than pH. So if you think about the alkalinity of the water, here's an example to help us understand how it works. If we have a 1 liter container and we irrigate that 1 liter container with 1 liter of water per week for 15 weeks, and the water quality has a pH of 9 and an alkalinity of 200 parts per million, then what happens to the container? We can see that that amount of water for 15 weeks provided the milliequivalents of base of 0.15. And milliequivalents is a way that we can just basically compare apples to apples, right? When we look at the alkalinity, those 200 parts per million provided an 60 milliequivalents of base. And that's the equivalent of applying 5 yards per cubic yard, 5 pounds per cubic yard of limestone. So even though we can have a high pH there, water pH will add only a little base, whereas water alkalinity will be the same as adding limestone. And this is something that we're talking again in the container. For those of you doing hydroponics, the story is very different because you do want to make sure that you adjust that pH way ahead of time to make sure those nutrients are, that pH is within the optimum range to have the nutrient availability. When it comes to container production, you want to pay a lot of attention in the alkalinity because that's going to react with what's in the peat, and that whole reaction will affect the nutrient availability in the container, right? So very different when we think about what happens in the water and then what's happening in the container. So alkalinity is a stronger base than pH when it comes to what happens in the container. Okay, so that's one part of the equation. So the other part of this equation that we're gonna tie together in a few slides from now is that we need to understand the fertilizer labels as well. So the nitrogen form is going to determine whether the fertilizers are classified as acidic, neutral, or basic. Okay, so if a fertilizer is mostly ammonium nitrate, ammonium nitrogen, then you know that the reaction is going to be strongly acidic, right? So think about, we were talking about having that dissolved limestone in the water. Maybe you want to match it to something that's acidic to make that reaction balance out, right? Nitrate, it's a weakly basic fertilizer. So that means that if you add fertilizers that are mostly nitrate, the reaction of the pH will remain relatively stable. Urea, I'm going to touch a little bit on urea when I talk about organic fertilizers, but urea is basically weakly acid because it has to go through many steps before it becomes available to the crop, right? So an easy way to look at acidity or basicity of fertilizers is most fertilizer companies and most greenhouse distributors, they try to make it very easy for growers to select a fertilizer based on their water quality. So you can pay attention to the letter of that reaction of that fertilizer, and that will give you a good indication. And then the bigger the number, the stronger the reaction to whichever direction it goes, right? So for example, if we compare this 13-213 with 17-3-17, you can basically know that this one has a much stronger basic reaction than this one. So the number is a relative number, so you can compare within fertilizers. And likewise, you can see that with the acidity, right? So if this one is an acid fertilizer, but definitely 2177 has a much stronger acid reaction, right? So those numbers give you a relative idea of how strong that reaction can be. But one of the things that I want everyone to know is that you want to make sure that, yes, you can trust the media company or the distributor that they did a good job with the lettering, but you also want to make sure that you verify that that's correct, right? So one of the things is you want to make sure, and that's also provided in the labels, and that's also provided by the greenhouse distributors. So you can always come here and, for example, look at this fertilizer and say, okay, this fertilizer is mostly ammonium and mostly urea, so that's why it's so acidic, because those two are acidic forms of nitrogen. Likewise, if we come to this one down here, or we can choose this one, which is a much more basic fertilizer, you can see 93% of this fertilizer is nitrate, and that's why it's such a basic fertilizer, right? So make sure you understand the label so you can make a real informed decision when you're choosing your fertilizer. Okay, so this is a little bit of the same, basically how you look at them and what are the big rough groups of how we see the fertilizers. But the important thing is really on this slide, right? We talked about water alkalinity earlier. We talk about nitrogen form and fertilizers. So how do we put those two together? So if we have a water alkalinity that's low, so something like 50 is considered very low. That means that there's very little in that water that's going to react with acidity. So you want to make sure that you use the fertilizer that's in the basic side, right? If you have on the extreme, if you have something like between 100 and 200 or 180, you know that you have some room. You can go with acid and basic and play a little bit there. Now, if you have levels this high, you usually want to make sure that you add a fertilizer that's relatively acid in a continuous basis, but you might also be interested in injecting acid at this point. And here we put the example of 2177, but I'm going to show you an example further. And one of the reasons you want to make sure that you add acidity as an injection mechanism as well when you are at this range is because if you're adding too much ammonium, that can be toxic to the crop as well. So the acid fertilizers have the disadvantage in terms of how acid you can select your fertilizers, right? Too much acidity in a fertilizer means that it can also be toxic because it has too much ammonium. So that's a very important consideration. Okay? So if you want to match fertilizer to the water quality, if you go to backpocketgrower.com and then you go under tools, there's one that's going to call fertilizer pH. And then basically you need to have your water test, and you can make your inputs there, and it's going to give you a warning and tell you if you choose this fertilizer with that water alkalinity, then the most likely reaction is going to be this. Or it's going to show you a green light saying, yeah, that's a good match. So very important that you look at that. And then the other tool that's in there in backpocketgrower.com is one that we created recently that's called WaterQual. And that's another one where you enter all your water quality information. You have to have your water test. And then it's going to help you make interpretation of what the water test problems might be. So it's going to highlight if something's too high, too low, and give you potential recommendations and directions of what you should be doing. So very good website that you should go into. And I'm going to touch just a little bit on organic fertilizers because this is one question that we get very often. I don't see many growers doing organic fertilizers in bedding plants, but I do get the question quite often. Okay, so what type of reaction should we expect from organic fertilizer? Is it acidic? Is it basic? What do you think? So just think about that for a little bit. And think about why is it that you think it could be either acidic or basic, and how would you match that to water quality? You don't have to tell me, but I just want you to think about that a little bit, okay? So if we look at the label of an organic fertilizer, we can see that it's not as specific as what we find in inorganic fertilizers, right? Because those are soluble salts. This one is mostly tied to an organic molecule. So here it says water-soluble nitrogen and water-insoluble nitrogen. And basically this is derived, this example, from oilseed extract. So the way nitrogen works, let's think about nitrogen cycle. It has two stages. So we have this nitrogen that's bound to an organic molecule. Microorganisms are going to start breaking that organic molecule. And the first step is ammonia. The second step is going to form some ammonium. So we talk about that ammonium being acidic, right? So when we have a nitrogen organic fertilizer and the nitrogen cycle is at that stage, then we expect that the reaction is going to be acidic, right? But the reaction doesn't stop there, right? Ammonium will convert into nitrate. And this happens with inorganic fertilizer too, right? So ammonium, regardless of the source, will go through this as well. The big difference is that in inorganic fertilizers, this reaction goes very quickly. And the ammonium doesn't always get converted to nitrate when you're using salt because it gets so quickly absorbed. So it doesn't have the time for this process to happen as a big bulk. Whereas here, because things are tied to organic molecules, they tend to be a little slower and more reactions tend to be occurring, right? So the ammonium will convert it to nitrate. We already said nitrate might be a basic, it's a basic reaction, okay? So the big issue that we have with organic fertilizers when we're trying to match it to water quality is that we don't know at what stage of the process we are when we're trying to make a decision, right? So let's say I have water with a very high alkalinity. It's very hard for me to decide if the organic fertilizer will stay in the ammonium form for very long. So organic fertilizers, they do work, but you need to make a lot of your own research in-house to make sure that they work for your own purpose, okay? And I'm going to expand a little bit on the organic fertilizers because this is also one of the things that we've seen happening in the industry, okay? Again, we have that same fertilizer. It's from Nature Source. It's a good fertilizer, and I actually have seen many growers who are producing leafy vegetables that use it, and it works really well, okay? But going back to you want to understand the label. So Nature Source, most of us relate that to the organic fertilizer. They also have a different line, and if we look at up close there, you can see ammoniacal nitrogen, nitrate nitrogen, urea, or other water-soluble fertilizers, right? So when you're trying to buy a product and you have in mind, maybe I want to do something organic, and you see something like this, just make sure that the reaction is going to be different. And I'm not, and again, the products work well. You just want to make sure that it matches to the situation you're trying to use it for, right? Because this specific fertilizer, it has a lot of ammonium and a lot of urea. So you would expect that to be very acidic and the reaction to be very quickly acidic. Very different from what this fertilizer, that things are tied to that organic molecule, so it's slower, okay? So make sure you read and understand the label, and then you can make a better choice of what you are trying to achieve in your operation. This is another example of vinca with ammonium toxicity. The example here, this grower, he had a pH of 6, and the alkalinity was extremely high, right? So in his mind, he said, okay, I'm going to use 27.7 because it's a very acidic fertilizer. The problem is that this might work well sometimes if you use it in warm months, but in colder months, it's a big problem because the reactions, again, they go very slow. And one of the problems is that the ammonium will stay very long as ammonium because there's no microbes to make it as nitrate, like we talked earlier. And then the other thing is that the plant goes very, very slow in the cold months, right? So as the plant is taking up water, that ammonium, it's also accumulating in the tissue, and the plant is not expanding as much, right? So then you are running into risk of ammonium toxicity. Okay. Again, this is one that you see more likely to happen in cold months. So that's when it comes to the type of fertilizer. Now, when it comes to the amount of fertilizer, you want to make sure that you target the electrical conductivity to inject the amount you want. So in this example, let's say we want to have a 1.8 millisiemens per centimeter. We know that the literature or the seed companies provide you that range. If you know that your irrigation water has 0.5, then you basically know, okay, I need to supply a 1.3 with my fertilizers to make sure that I'm within the optimum range that the crop can tolerate. And most of you know how to do this, but basically you say, okay, I need to put, we said here 1.3. So let's say we're using this fertilizer or this one, then you know you have to apply 200 parts per million nitrogen. And this is one of the good examples that it's important to look at, because if a grower tells you, oh, I feed my crop with 200 parts per million nitrogen of this fertilizer, it's not always the same thing that you can do if your neighbor does it, because their water quality might be different. So important to consider that you can listen what other growers do, but make sure you tailor that to what is going on in your operation. And this is just an example of what happens when you apply too many salts, right? You can see that the burning of the leaves occurs very clearly and very quickly too, okay? So now we're gonna move into the third aspect, and is monitor the pH and electrical conductivity of the substrate. And we talked about it slightly before. Before we were talking about what we do when we get a new batch of growing media. Right now we're talking mostly about what to do in the container, right? So why do we measure electrical conductivity in the irrigation water? It's going to be a good indicator of whether there are changes in contaminants. And by contaminants here, I mean anything that have changes during the season. So if you have in the Northeast, sometimes we've seen spikes in chloride, and a simple test of electrical conductivity might help you pick that up at an earlier stage. Why do we measure the pH of the irrigation water? You can measure if the acid injection is appropriate, if you're injecting it. If not, it's again a slight indicator of what's going on. Okay, and it's especially important that you measure the pH of the irrigation water if you're injecting that acid to control that high alkalinity. Why electrical conductivity of the growing media in-house? It's something that every grower should be doing, because it's a good indicator of the levels of nutrients and salts in your container, right? Again, if you know that, if you see spikes before the problems, then you're more likely to be able to control. And then the pH of the growing media, it's again a good indicator of nutrient availability. You again want to make sure you protect yourself before the problems happen. Many growers, they tend to just measure this pH and EC when the problems arise, and that sometimes, again, it's too late. So make sure you always have the same person at the same schedule doing those measurements. So let's say you decide, okay, every Wednesday morning, this person is going to measure pH and EC of 5 containers in this section or 5 containers in every section. Whatever it is, make sure you have that as part of your routine. If it's not part of your routine, you're gonna let it go and just do it when the problems arise, and that's sometimes too late. Okay, so we also want to measure the EC of the nutrient solution, and we can do that by just collecting samples at the emitter. And this is very important because you want to make sure that you're dosing the right amount of fertilizers. So a quick EC measurement can tell you if the injector is working properly, if you mix the right amount of fertilizers. And then why do we want to know the pH of the water when we're mixing agrochemicals? It's because some agrochemicals work better at a specific pH. So you want to make sure that you get the most out of your pennies. So if you're applying a chemical that most of them are pretty expensive, you want to make sure that the efficacy is at its prime, and pH might affect some of them. So when we're trying to choose in terms of growing media, what test to do, you want to make sure that you can't test every crop. So that's something that I'll put up front, because sometimes people, it sounds like I'm trying to say you have to measure every crop. No, you have to choose those that tend to be the most sensitive as your indicator crops, and you want to make sure that you do it consistently. So once a week is the ideal, every 2 weeks at the very least, but I think weekly would be the perfect timing. And then for every method, the test results vary. So let's make sure that if you decide, okay, I'm doing large containers, so I'm going to be doing pour through. So then you can just collect the leachate. Make sure that you always compare your number to the pour through in the tables of reference. So if you have any of those floriculture books, or if you look at the references from seed companies, they always tell you what type of method they're comparing it to, and they give you a reference of how that compares to other numbers. So for example, pour through EC tends to be slightly lower than saturated paste, so you need to make sure that you know that, to make sure that you're comparing it to the right reference. Example, iron deficiency. For example, in this case, you know that petunias are prone to iron deficiency, so you know that the crop tends to be problematic. So what do? You start by measuring the pH and EC of the substrate in-house, right? Because that's the fastest thing you can do. So you need to make sure you take both measurements, because if the pH is high and the EC is within the acceptable range, you can infer that the cause of the disorder is the high pH and not insufficient fertilizer, right? Even though the plant looks hungry, it's not a lack of fertilizer, but it's that the pH is off and the nutrients are not available to the crop. So your reaction should be to adjust pH. If the pH is within an optimum level, but the EC is low, then you know that you're not providing enough fertilizers, and then you can start by putting out more fertilizers. So very important that you measure both things to make sure that you're targeting the right cause, not just the symptom, right? Match the management practice to the cause of the problem. And then again, you always want to validate your results with complete nutrient analysis. And you want to make sure that you adjust once you get those. It usually takes like 2 days to get those results back. So that's why you do your measurements in-house, but you can readjust based on the results that you see there, okay? And this is just an example of a little bit of what I said, but make sure the different causes are here. So it can be either just insufficient iron. You can only know that by a complete nutrient analysis. Is it too much limestone? And that's because the pH is high. Is the water alkalinity too high? So you want to make sure that you match that to the cost, okay? And just a little bit more about iron here and the importance of pH is that adjusting the pH is more effective than applying iron alone. So here are examples of the different iron types, and you can see the different concentrations of iron applied for each of the different forms, and then the different pHs. You can see that it's more important to have a lower pH than more iron, right? So in this case, you can apply 2 parts per million of iron and your crop's still not as good. Whereas if you just lower the pH and apply very little amount of iron, you can recover that crop much better. So pH, it's very important for you to keep that in track. And then here, just again, a similar example that if you're not adjusting the pH, in this case, the pH was very high, 7.2, you can see that it's going to take a lot more iron for you to recover that crop and get an optimal level. So you might as well, again, go back to adjusting the pH. So general recommendations about monitoring: make sure you're consistent on where, when, and how you collect those samples. I would also add who collects the samples is important. You want to collect multiple samples. You want to make sure you calibrate your equipment, because if you're not calibrating your pH and EC meter, it's like not doing anything. So make sure that gets calibrated, and make sure you keep your records and make your decisions based on numbers, right? Not just because you see a plant with iron deficiency doesn't mean you need to go apply iron. And I hope you can take that from here today. And then finally, just a few more notes: how to adjust the fertilizer rate and type to manipulate pH and EC. Again, we talked about this already, but just to overemphasize that you want to use the nitrogen form to adjust the pH. Under extreme circumstances, then you go to your second layer of tools: acid, flowable limes, or iron when the elements are insufficient, right? I'm going to skip this one because we already talked about this. Another thing that it's an interesting tool is just how we water our crops and how that has an impact on pH and electrical conductivity. So what we're looking at here is that this one here, what we're looking is substrate electrical conductivity, and here it's substrate pH, right? So what this is telling us is that as we increase the amount of leaching, let's say we have too much salts, we're going to apply a lot of water, and this is increasing the leaching fraction. That obviously we know that lowers the substrate electrical conductivity, okay? The important thing to consider is that as we're doing that, the thing that's happening is that the pH will also go up. So keep that in mind, that other practices such as how much water we're applying will affect how the pH and electrical conductivity react. And this is a slide that Ryan Dixon gave to me. He's now at the University of Arkansas. And the explanation for this is that if you leach with clear water, it's going to wash away the salts, right? So let's say we have all this acidity here, right? And then these are elements that are attached to the peat. If you're watering with a lot of water, right, we're leaching to get rid of those salts get washed out. And then that acidity that was originally free in the solution now gets attached to the particle. And what's left here is that we have a low concentration of hydrogen ions, but the pH around here goes up. So if you add fertilizer, that's also in general going to decrease the pH, right? Because if you're adding a lot of salts, those will displace those hydrogen ions, and then you expect that the pH will go down because those hydrogen ions will be free in the solution and not close to the root zone anymore.